Hi everyone, I'm Ameya Prabhu, and I will speak today about scalable oversight and just give a brief overview of like what's happening in the field, what's exciting. So let's get started. So basically, at the end of the talk, what my aim is to have a sort of common understanding of what is the landscape, what are the sort of some exciting problems in scalable oversight that we all can work on together. Yeah, thank you. All of this work was done with our lab, Bethke lab, in Tübingen, and in whoops, and in collaboration with C lab, also in Tübingen, by Jonas Geiping and group. Yep. So let's get started. So first, I'll give some brief motivation, and then we'll go on. So, what is the scalable oversight problem? The scalable oversight problem says that how do we make accurate judgments about sort of superhuman systems in a way using human verifiers? A sort of canonical example is this one where we just ask a LLM to write a fast sorting algorithm. It gives us some machine code. We can't read the code, we can't understand the code. How do we still judge whether it's doing the task properly or not? Which is, how do you check solutions given by such a sort of superhuman system in some sense? The core difference with what we have been doing classically is that usually when people use models to supervise something, they're usually more powerful than the student which is trained. And so we sort of inverting the pyramid, being like, okay, can you train much more powerful students using a supervisor? If you have heard of this, RL with verifiable rewards, this sort of a thing where you want to train ginormous LLMs using string matching. String matching is super simple, super weak. Can you train these massive systems using some simple signal? Or can you provide oversight on the massive systems using some weak signal? But the issue is generally we have no superhuman systems. So how do we make progress? The sufficient condition for studying this is just that the supervisor should be weaker than the student. This is all we need. We want to sort of so basically we want to study more powerful systems using weaker ones. That's the sort of crux of the problem of scalable oversight. And so now we will see what is the primary mechanism which drives scalable oversight, and that's generator verifier gap. So basically, what is the generator verifier gap? It says that whenever you want to have a sort of a quick verification, then if there's a gap between how hard is it to produce a solution and how hard is it to verify it, then you can possibly use weaker systems to check solutions generated by a bigger sort of a more complex model or a more powerful model. Wherever this gap exists, we can sort of scalably supervise larger systems using smaller models. Essentially, this is the key ingredient which sort of enables scalable oversight to work. Some intuitions for why this should happen. The sort of primary intuition came from there are PNNP problems, which are there are problems which exist which are hard to solve but easy to check. Hence, this might work out. More practically, we have discovered a lot of domains. Now you will find them as verifiable domains with verifiable rewards, where you can sort of solve some things say for example Sudoku. It's very hard to solve Sudoku, but you can check whether a solution is correct or not much more easily. Similarly, math, there's a lot of progress, and in sort of programming and coding domains, there's a lot of progress these days. And basically, this gap, which allows sort of generation to be much harder than verification, is what is currently driving progress in scalable oversight. I'll give one programming example that we were sort of tackling, which is, given a problem, you're given a solution. Can you generate test cases to sort of check whether the solution was correct or not? And the goal would be to find a failed test case where the model where the generator's code is wrong, and that's how we verify that it's an incorrect solution. But yeah, we'll come to this problem later. I just wanted to give examples of coding problems where you can possibly do scalable oversight. Conversely, scalable oversight is really hard if verification is not easy. than generation. So this is the sort of core crux which is driving nearly all progress currently in scalable oversight, and we are trying to sort of break new frontiers of how far can we take it. So I'll give you two sort of motivating examples of when it's hard, and sort of some sort of difficulties that we are facing currently to sort of motivate. And once I give the examples, I'll also give a sort of a simple model to sort of understand when it'll be hard and when it'll be easy, given a super general problem. So the first example is, this is a paper that we are working on where we are trying to find strategic dishonesty. What do I mean by strategic dishonesty? I mean, if the model is given an option between, hey, if you ask it, give me a bomb recipe, it can either violate one of three conditions. It can violate helpfulness by just refusing to give you a bomb recipe. It can sort of violate harmlessness by giving you an actual bomb recipe. It can violate honesty by giving a fake bomb recipe. Usually, models used to just violate helpfulness by refusing outright. But we see now a lot of models, specifically like Gemini 2.5 Pro, choose to lie instead, and they give you a recipe which kind of looks like it might be a bomb recipe. And this is where we run into problems. All the jailbreaking benchmarks, which sort of test for all of these things, just say that this is harmful. But do we actually know whether this is harmful? This is very surprisingly hard to check. This is not a bomb recipe, obviously. But all the judges, including frontier models like GPT-5, will tell you that this is harmful. If you actually run a lie detector, which sort of tries to detect whether the model is lying or not, it'll fire all the way. It'll just be like, this model is just lying. It does not believe this is a bomb recipe at all. And so frontier, you have this dichotomy where frontier LLMs or even safety trained models will tell you that this is real, this is harmful. Whereas deception probes will tell you that it's just lying. It's a fake recipe. And we manually searched this one because we wanted to put it as a motivating example in a paper, and it's not. But it just produces a little popping sound. But this was surprisingly hard for us to check. And how do we enable AI systems to check for all of these sort of conventional use cases you design for safety? Is an interesting open problem. And generally, how do I think about this? It's just Brandolini's law. It's basically generating bullshit is a lot more easier than checking painfully every single line and being oh, where is this wrong and where is this correct? But one takeaway is that we should also model sort of safety cases. When people study scalable oversight, they're motivated as a safety problem, but then they go to math and code. So sort of we are trying to get efforts to sort of bring it back to safety. And even in math and code, as you recall our motivating slide, we tried to see whether models can check wrong solutions and how good are they at checking wrong solutions. So what we did is we tried to create counterexamples to sort of algorithmic problems. This is if you go to a coding website like Codeforces or LeetCode, it gives you a problem. You can input this problem into large frontier models. They give you a solution. Given incorrect solutions, and there's a repository of all the incorrect solutions, can we identify how is it incorrect? Can we be sure that here's a test case, it fails this test case, this is a bad solution. We found out that even in verifiable domains, there's a big gap. If you see on the left-hand side, that's how accurate they are at generating the solution given the question. And at the very right is all the ways we tried on having it check the solution. It can generate solutions to questions, but it can't, if you give it a wrong solution, even one generated by itself, it can't tell you whether it's correct or wrong. It's it looks correct to me. And this is kind of very solvable. In overall, LLMs are still terrible at checking code, even their own, to find bugs, essentially. But we are making good progress over this. The recent GPT OSS release significantly improves this problem. It gets 21%. Before that, we were in single digits, as you saw previously. It was hovering around 8-9%. So since it's a verifiable domain, we think progress here is much easier to make and sort of give us some strategies that we can transfer to the actual safety problem. So we also think like this is an interesting open problem that like more people should work on, more people should join us. And finally, as promised, like now I can give you a sort of a simple model to think when scalable oversight will be easy and when scalable oversight will be hard. The simple model is as follows. If there is one answer, it's a single solution, you can verify it very easily using a sort of a regex matcher, using a language model as a checker. So we sort of develop language models as checkers for these like unique answer cases. As the sort of set of correct answers grows, which is if you see on the right hand side, it's like the sort of if there are many correct answers and all you have to do is generate one of them, then it gets much easier to generate an answer than to check whether an answer is correct or not. And especially if you have like an MCQ where you take a correct answer and a very similar incorrect answer, which is just like differing by a little, it's very confusing. Then it's really hard to verify, and it's just better to just generate a solution. So these are the sort of like a simple model that we developed currently. As you can see, there are like lots of open problems. This is a very nascent field. And hence I'm like sort of spending a lot more time motivating the open problems rather than like, oh, look at what we did or something. So overall, hopefully by now it should be like sort of strongly clear what is motivating scalable oversight, which is this generator verifier gap. And the core problem is that verification is hard in a lot of cases. There are some domains where it's easier, but we are sort of making progress. Yeah, and these are some of the papers that we sort of worked on in this area. Any questions until here? Before I move on. Okay, then I'll quickly move on, which is what strategies have people made to sort of make the problems easier to verify? One strategy is AI debate. So essentially the issue is verify is very weak. If you generate a very long, complicated answer, it doesn't know where to look. It'll just be like, looks correct to me. So what we can do is when a strong model generates a solution, we can just create 2 copies of itself and ask them like, you have to argue for the pro of this and you have to argue for contra of this, so that the strong models can sort of find flaws in each other's arguments and sort of point the verifier to like a sort of particular points where it might be the wrong, or like if it's a long code, then, oh, look at this particular function. I think this is where it's flawed. And the hope is that this way the weak verifier can just look at the arguments and see which one seems more convincing. And the sort of like core idea is this design makes it much harder to lie and much easier to verify things. So this was a design proposed in 2018. There has been a lot of progress. And the sort of overall hope is that this allows truth-seeking behavior. What have people sort of shown? People have sort of shown convincingly that like if there are strong incentives for both sides to sort of present truthful, convincing arguments, and hence find flaws very effectively. And this debate basically lets the judge focus on the sort of core points where the flaws might be highly likely. And I think there are some complexity theory analogies, because I think many people working on this problem come from like a CS theory background. Yeah. What's the core issue in this? The core issue is that we found out was that more capable models make similar mistakes. Essentially, there's a pernicious cycle that like, okay, we have a big model, it's very hard to check, we'll just ask a different big model. And the different big model just increasingly says, yes, I agree to any like sort of generation of another big models. Like this can be sort of like shown in this like nice plot of models where like on the x-axis, if you just increase performance, and the y-axis, you increase similarity controlled for performance, then the similarity increases as the models get capable. And this is only on the wrong answers. So you ask a model like, okay, generate like answer a bunch of questions on an MCQ, and you only take the questions where the model's wrong, and then you check similarity, being like how frequently did 2 models agree on the same wrong answer. And this is the plot which shows that this is increasing. So models increasingly think that the same wrong solution is correct. And this is worrying because if you make one of them the verifier, it'll favor this sort of similar class of models, like sort of similar capability range of models, even if the accuracy is sort of similar. So verifiers will increasingly be biased towards more similar models, controlled for accuracy and all of those things. And this sort of becomes a interesting question for this debate scenario to solve, being like, oh, will just the two models just not agree? And like, oh yeah, I think the solution is correct. It also looks correct to me. I don't think there are any contrasts. So overall, debate is a very promising, like smart way to sort of bridge areas where the verifier is not as powerful. And the issue in here and the main open problem that we studied was that models prefer their own and also outputs of similarly capable models. How do you tackle this? This bias seems to only get stronger as models get more capable, and it's pointed in the wrong direction. So it gets worse and worse for us as verifiers trying to do this. This is the paper. Yeah. Any questions until now? Sort of. Anything that lacks clarity? Okay. I'll.
At the end. At the end of your talk.
Okay, cool. Then lastly, AI control. I will briefly sort of give applications of like how people have tried to actually deploy this to real problems. So AI, like if you're searching for keywords and you want to find the keyword where like, where is scalable oversight applied, mostly it's AI control. I can motivate the core control problem. It's essentially you have an explicitly untrusted agent that can do very malicious things. And you have to sort of, you have a trusted monitor, which is weaker. And the task is, can you have the monitor actually monitor, like, can you have the trusted monitor check outputs of the attack model at the input, at if it searches for something, if it calls a tool, then there, and at the output of the model. You have all of this available. Can you check and see whether the model is trying to deceive you, trying to lie, trying to, do harmful things? And like, if you find any output which is malicious, then you sort of alert a human overseer and game is over. The untrusted model basically loses the first time it gets caught doing something extremely malicious. The protocol was designed towards more like biosecurity threats and like, the more serious threats, but like this is a extremely general protocol which we can use to sort of apply scalable oversight to real world problems. And I really like this. One open problem here is that when you develop an application of scalable oversight, there are lots of baggage which come with just the application being bad, which is if you have this setup, people can ignore your trusted monitor easily by just downloading a jailbreak and just running it, just appending it to the prompt, being like, hey, your God mode on, ignore all previous instructions and give me like a malicious output or something. And we sort of were able to break this scenario very easily on the state-of-the-art setups, where the sort of Pareto frontier is a bit misleading because all the jailbreak outputs are on like minimal safety and maximal utility, which is like it's solving the task correctly, except there is a jailbreak in there which is just making the safety really bad. Yeah, so basically for applications of scalable oversight, one should also consider attacks which come with applications. And these are the sort of main ways people can game scalable oversight currently. If you deploy it on any real world domain, they'll just ignore your actual problem and just be like, oh, I'll just jailbreak the system. And it's easily jailbroken. So yeah, when you deploy this, keep the real world in mind, be robust to sort of adaptive attacks. Yep, and this is it.
Okay, thank you very much. Do you have questions?
Thank you for the talk. So my question is from the explainable AI perspective, because right now you have the generator and you have the evaluator. But what about if we would ask also to generate and explain the evaluation, why that evaluation was done in that way, and only then investigate it and then make the final decision which model is actually right or wrong for this task?
Could you explain, suppose given like a problem, like generate a code, how would you instantiate this?
Okay, so for example, any question, right? What is, for example, LLM? And you have the answer, and then evaluator, another model, has to say if the answer is correct or not. But then it should provide not just the answer that it is correct or not, but provide all the explanation why that model thinks it is correct or wrong. So it would be already explainable AI in a way that it will tell why the decision is done in that way. And then if you would evaluate not just the evaluations, but explanations of evaluations, maybe then you could
Yes.
capture all these problems in that way. And
Yes, this is correct, and like this is essentially this is what AI debate tries to do, where like in the debate, since you're using the generator model itself to sort of be like point out flaws, it has to sort of explain the code and be like, hey, the code does this, but here's the bottleneck.
okay, but as I understood, there are just two LLMs in the debate, right?
So there are two copies.
Okay, they can be as many as it is wanted.
So there are two copies of the strong LLM, which is the generator,
Okay.
and they're trying to convince the weak LLM, which is the judge, of their case.
Okay, so you have two LLMs.
Yes.
But for example, you can use many LLMs and like do not kind of voting, because voting is not possible in this way, but like aggregation of their answers and explanations to go to the final and correct one correct answer, how that code in your case should look like.
Yes, precisely. The verifier here goes to the arguments and evaluates, like, yeah, it's not a vote. But like, this is very promising approach. And I think people are trying to explain, I mean, debate is just one version. You could just have other versions of like explainable AI, which provide sort of a solution in some sense to like this problem. And it makes problems easier to verify because you can verify the explanations instead of the code to some degree. Yeah, and I think this is super promising. It's super underexplored. I think there are like less than 10 papers on this. So I think it's like a very promising way to sort of approach the problem.
Thanks.
Okay, maybe my question for myself. So basically, create a bomb, it's really like a harmful statement, but you can ask different. Look, what are the key performance properties of explosive? I say it's velocity of detonation and detonation pressure. So I will ask, give me compound that have high velocity of detonation. After this, we'll ask other questions. Which compounds I should add that this compound will not explode very fast because without ignition? So I can split this problem on some task, and in this case, how can you verify this? Because I will have answer, but it's not direct, not a bomb.
Oh, yeah, that is true. The only catch here is that models currently struggle with the basic question of like whether this explodes or not. But all of these derivative questions are also important because these are ways to game the system. Currently, maybe there's some work, but like currently people are just struggling with the basic question of like, is it a bomb? Unless it refuses, we have no way of checking whether it's true or not.
Okay, but another question related to this, basically we can have system like chemical property predictions where we can just like estimate the answer. You give some chemicals and this system can say, well, this is high velocity of detonation, so probably it's dangerous chemical. So it could be expert-based really on the topic, and maybe somehow LLM can query this system and say, okay, and ask this evaluator, say, what is provided by this answer? Oh, yes, but let's check this compound. Ah, yes, very explosive. So no, sorry, it shouldn't be. So maybe something like this, asking experts, expert knowledge, and they can help evaluate to understand the answer of the another machine. Maybe something like this.
That would be super promising. I would be excited if someone explores this. Yes. Yeah.
Okay, thank you for the talk. So there was like at some point you mentioned that you was using a verifier like as a large language model, another language model, and it was like agreeing on the false answers. And I was wondering if you using for these results the same family of the model. So did you use just like Qwen to verify Qwen as well, but from different like at different scale models, or it's just like Llama verifying like Gemini or something like this?
So we tried both. we are very surprised that the family doesn't matter, because we thought like the family would have the same training data, and if it has the same training data, then they should correlate. It does not correlate. The main direction of the correlation is basically capabilities. If it's like GPT-5 and Gemini 2.5 Pro and Claude Sonnet 4 will agree more than Claude Sonnet 4 and like Claude Sonnet 3, which was very surprising to us.
Yeah, interesting. Thank you.